here, they give you a function. Oh, 9 minus x is kind of boring. Let's do 28. So 28 gives you the function g of x equals x squared plus 1. And then it gives you the interval 1 to 3, and it tells you to use 8 rectangles, use left and right endpoints to find approximations for the area. So here's my function. My interval they give me is 1 to 3, and they want me to use 8 rectangles to find the area under the curve from 1 to 3. So what does g of x look like? What's my picture here?
It's a parabola moved up one.
It's a parabola shifted up 1, right? So let me draw something like this. That's kind of lopsided. Okay. So this is x squared plus 1. Then on the interval 1 to 3, I want to fit 8 rectangles. And it tells me to use left endpoints and right endpoints, which is a little different than the way we talked about this before. So let me talk about that. Left endpoints means you're going to break this. You're going to break this interval from 1 to 3 into 8 rectangles. Right? So we'll be able to make this. You're going to break this into 8 rectangles, and for each rectangle, you're going to use the left side of the width. Right? So you always go up to the graph on the left of the rectangle. That's what left endpoints means. In this case, left endpoints is the same thing as lower sums because we're always saying how much. This is left endpoints. Left endpoints just means you go up to your curve on the left side of your width. Now, it just so happens that left endpoints happens to be the same thing as lower sums in this case. Left endpoints is not always the same thing as lower sums. Because if I flip my graph over, if I have this picture, like this, then when I do the left endpoints, I actually end up above my graph. If I go up on the left and draw a rectangle, I end up above my graph. Okay, so left and right endpoints doesn't necessarily have anything to do with above or below the graph. It's just another way to designate which rectangles to use. But what do I need to do? To find this area of these 8 rectangles, what kind of calculations do I need to make? You need the width of each rectangle, right? So how do you calculate the width of these rectangles? Yeah, so the width is always the same formula. For the width of your rectangles, you take the total distance that you're covering, the total length of the interval, 3 minus 1, and you divide it by the number of rectangles, which is 8. So 2 over 8, or 1/4. So then, for the height of the rectangles, what are you going to have to do? What are you going to plug into the function?
1/4.
Are you going to plug in 1/4?
No, squared.
So you start, first you plug in 1, and then what do you plug in after that?
2.
No.
Well, 2 would be all the way in the middle.
1/4.
1 plus 1/4, right?
Yeah.
So 1 1/4 or 1.25. And then you add a fourth again. So 1.5. And then you add a fourth again. So 1.75. So you add a quarter each time to get the correct x value to plug in. So your area will be equal to the width of the first rectangle, which is 1/4, times the height of the first rectangle, which is going to be 1 squared plus 1. Right, for the first rectangle, my left endpoint means I go up on the left of the graph, which is at 1. I go up on the left of the rectangle, I should say. Then I move on to my next rectangle, so I'll have 1/4 times 1.25 squared plus 1. Because I moved over exactly 1/4. So this came from taking, this 1.25 came from taking 1 plus 1/4. So that would be my second rectangle. My third rectangle would be 1/4 times 1.5 squared plus 1. And this guy comes from taking 1 plus 1/4 2 times. And you continue in the same pattern until you get 8 rectangles. 1/4 times 1.75 squared plus 1. 1/4 times 2 squared, excuse me, plus 1, right? Because if you add a quarter again, you get 2. 1/4 times 2.25 squared plus 1. 1/4 times 2.5 squared plus 1. 1/4 times 2.75 squared plus 1. Do I keep going? 1/4 times 3 squared plus 1?
8 rectangles.
No, that would be a nice rectangle. Right, if you did 1, 2, 3, 4, 5, 6, 7, 8, that'd be a nice rectangle. So that's too far. We only want 8 rectangles. So then you'd have to go in with your calculator and calculate all these and add them up. But I certainly wouldn't do any more of this by hand because it's just kind of wasted. Calculator.
Would it be easier to write this as a sigma notation?
What's that?
Would it be easier to write this as sigma notation? Can you even do that?
You could, if you wanted to write, I mean,
Would there be any benefit to doing so?
I don't know. If you wanted to write this in sigma notation, you would have to take I from 1 to 8, and then you would put 1/4 times, and then what's the pattern here?
Plus 1.
You're always adding a quarter, right? So you'll put 1 plus 1/4 I. Oh, you'll have to take, yeah. Square 1/4, you'd have to do it like this. And then you'd have to square this plus 1. You see why did I change this from 0 to 7?
Because you're starting at 1.
Because your first point here is 1, right? So now if you plug in 0, you have to get out 1. If you start at 1, then it won't match up correctly. You could then try to use your formulas, I guess, to sum this up with the formulas, but I don't think it's going to save you any time over just plugging this in your calculator. As far as tests and quizzes go, 8 rectangles is a bit much. I mean, the more rectangles you use, the better the estimate, but the more rectangles you use, the more time you waste. So, I'll stick to 4. Although, to save yourself a little bit on the calculations, you could factor out the 1/4. Right? You could write, since all of these have a 1/4, you could take the 1/4 out, and then just write the height in each case. 1 squared plus 1, plus 1.25 squared plus 1. Plus, and you keep going until you get down here. That would save you a little bit of calculator work. If you won't have to do times 1/4 every time. But at this point, it's really just a punching numbers in. Calculator. So what changes, because it actually asks you 2 questions. It asks you to use left endpoints and right endpoints. What's going to change for right endpoints? What do you think that means?
Does your number start from 1?
So instead of going up on the left side of your width, instead of going up to the parabola at 1, you're going to go up on the right side. So you're going to go up here and then go over like this. So I'm going to go up here. Go over like this. So it ends up being an overestimate. This, in this particular case, this is the same as what we call upper bounds. So then, to calculate this, what would you have to do? So you'd use the same width, and you still have to add up 8 things, but instead of starting at 1, you'd start at 1.25. And then instead of ending at 2.75, you'd end at 3.
Would it be the same?
Answer?
No, like when you do it, would it be the same distance from the actual to the left hand?
Oh, that is an excellent question. I don't think so. I think because, I mean, if you zoom in on this, you just take this part right here, you sort of zoom in on it, you'll have this parabola bending upward, and the blue rectangle is always on top, like this, and the green is an underestimate, like this. But this isn't a straight line. Right? If this were a straight line, then they would be exactly, you'd have as much overestimate as you had underestimate. But since it's bowing upward like this, I think the underestimate is going to be less because you have less error here than you do here. So that has to do with the concavity, right? Which way it's bending. Okay. Yes, Miss.
Section 4.3, number 3.
So, yeah, let me look at this for a second. So I gave you a limit definition of the definite integral last time. So I'll do number 3 in a second, but I have to write this definition out first. The definite integral is this guy from a to b of f of x dx, and as a limit, it equaled this. Limit then goes to infinity of the sum from I equals 1 to n of f of a plus b minus a over ni times b minus a over n. This is the simplified version because it assumes you have equal width for your rectangles. That's not a huge deal. So in number 3, they give you a particular function to work with. They say find the integral from 2 to 6 of 8 dx. Now, geometrically, do you remember I kind of described the definite integral in 2 different ways. In terms of geometry, what does this integral mean? What does it equal? The definite integral is the same thing as the area. This is the area under the curve y equals 8. Okay? So if you were using the area definition, you would draw y equals 8, which is up here, and you would find the area from 2 to 6. Here's 2. Here's 6. This is y equals 8, so it's asking for this area. What's this area, by the way? 32. Yeah, it's a rectangle, right? You have two 2 to 6 on the bottom is going to give you a rectangle of width of 4. And then your height is 8. Length times width for the area of a rectangle is 32. So at the end of the day, we should get 32. And I advise you, unless the instructions say use the limit definition, you should try anything else first, okay? Because the limit definition is obscene, right? It's just out of control. So, using the fact that the definite integral is area under the curve, we know the answer to this should be 32. But we didn't use the limit definition to get it. So let's go back and try the limit definition. This one's not too bad. So the limit definition is this bad boy. Like this monster. So the definite integral is going to be equal to the limit as n goes to infinity of the sum from I equals 1 to n of this. So what's a and b, and what's f of x in this particular case? A is 2, b is 6, and what's f of x? What's our function? Just 8. Just y equals 8. So in my sum, I have to put f of a plus b minus a, which is b minus a is 4. So I'm just substituting. A is 2, b minus a is 4, n is n, I is I. And then on the outside I have 4 over n. Fortunately, because our function is so simple, this guy is going to simplify very nicely. What happens when you plug 2 plus 4 over ni into this function? If f of x equals 8, then what's f of 1? 8. What's f of 2?
8. It's always 8.
So what's f of 2 plus 4 over ni?
8.
So this whole thing, because there's no x in the formula, is just 8. The 4 over n, I can't do anything with that. That sticks around. Now, how do we actually evaluate this sum? What were the tricks we used?
Pull 32 out.
Pull out any constants. Right? Factor out any constants, anything that doesn't have an I. So there's 32 on top and n on bottom, and neither of those have an I. So pull them out. What would be left in your sum? 1. Right? You have to have something back, so when you multiply, you get back to 32 over n. So you have to have a 1 left in there. Then you use your formulas. Remember, we had all these formulas, like the sum of 1 from I equals 1 to n equals n. Or the sum of I from I equals 1 to n equals n times n plus 1 over 2. We had all these formulas. This guy, because it's just the sum of 1, is going to end up being n. This formula. The n's cancel. So what's your limit? 32, because there's no n's left. So the limit as n goes to infinity will just be this number. Same as what we got here. With a lot more symbols.
Do we
more
need
confusing.
Do we need to memorize those formulas, or will you give them to us?
If you need them, I will give them to you.
What about the A to B? Like
This?
Yeah.
I probably won't give you that.
But I won't be able to. Just kidding.
I have no idea. I have no idea. I don't know what I'm gonna do for this test, I'll be honest.
I'm gonna make it very easy for you.
I've been trying that, apparently doesn't do anything, so
You could just not give it.
you need to give me more advice.
Take home final.
Yeah, I know you guys do take home stuff, alright?
We can work with this idea. I like it.
So using a limit definition to evaluate an integral is not a skill that I value highly. It might be something I'll give you on an extra credit, but it won't be something that I'll test you on for actual credit, you know, because it would kill a lot of people. This one's pretty nice though, because it's just a constant. However, it's really annoying to know I can get the answer so quickly with the area definition and then have to do this. The important thing now, though, is that we got this fundamental theorem of calculus that allows us to do these definite integrals by taking the antiderivative and then plugging in the limits. So let me do some review from 4.4, which we started last.